Hi, guys. Thank you for joining. This is Essence of Science, and today we're talking about everyday science and how magnets work. I'm Amanda Armagost.
And I'm Dr. Abbasi for Essence. Now, I don't believe there is a single boy that hasn't been, um, you know, fascinated with magnets. Did you ever work with play with magnets when you were young, Amanda?
I didn't really play with magnets. I guess I had those rocks that would they were kind of magnetic rocks, but or I guess I would play with like a thin plastic or something and move the magnet around. And we also had these plastic blocks that were magnetic on the corners at my daycare, and we
Hmm.
would build houses out of those blocks. But that's pretty much the extent of my magnet playing.
Yeah, and those rocks that you were talking about is actually how we discovered magnets. In the ancient time, even they knew there are certain rocks that they repel each other or they attract each other. And not long after that, we discovered that those rocks or certain element of those rocks, if you just leave them be in a like a on a leaf or on water, they orient themselves in certain ways that you can use that to find your orientation. So this is a very, very old observation that we have. Did you ever think why the magnet? Like, what do you feel when you bring two magnets? Did you ever think about that?
Yeah, I've thought about like the pressure that you feel when you're putting two magnets together, like either
Hmm.
them pushing apart or pulling together. But to be honest, I've never really thought about or wondered why are they doing that. I've just
Hmm.
observed that they are doing that.
Yeah. Well, in your home, where do you think in your home there are magnets that right now making your life possible?
Um, I know that there's magnets on the corners of
Corners
like
of what?
the walls. There's like these metal things that are magnets. So then the walls are more strong on the corners, and when you hit them, they don't get dent like the um that material, the sheetrock doesn't get damaged.
Oh, that's not a magnet. That's just a metal. That's
Yeah,
just
but it's a magnetic metal. You can put magnets on it.
well, it's a magnetic metal. Yes, yes.
Mhm.
But it's not actually that metal. It's just steel. That's just a steel sheet that they put around the corners. And obviously, you just mentioned that there are magnetic metals and there are non-magnetic metals.
Mhm.
And did you ever think, obviously iron is magnetic and steel is a alloy of iron is magnetic, but there are two other metals that are magnetic and but all the other metals in the whole universe are generally not magnetic. But did you ever think about that? What makes something magnetic or not magnetic? Did you ever think about that?
No, what makes something magnetic?
Yeah. Well, you notice that on the corner of the walls to make it strengthen it, they under the plaster, under the gypsum or whatever plaster what they use, they put a corner block that's made of steel
Yeah.
to make it stronger. Obviously, steel or iron is magnetic, and then the nickel and cobalt are as well to some degree magnetic. But I'm sure you have tried. One of the way to prove that something is not gold is use a magnet because gold is not magnetic. That's the
I
first
never
thing they do. If you try to go and sell your gold to somebody in a pawn shop, first thing they do, they put a magnet on it. But obviously, not everything that there are so many metals that are not magnetic, like aluminum is not magnetic, like thin or thin or um, copper. They're all not magnetic metals and so on. But and that is as well that we discovered early on that there are few metals magnetic and there are lots more metal that are not magnetic, but it just happens to be those metals that are magnetic, we use them more and more in our everyday life, like iron.
Why?
Mm, yeah, what? No. Um, let's now you have to make me go thousands of years back. I cannot answer that without going 1,000 years back. The human history has a so-called Stone Age, right?
Mm-hmm.
What is the hallmark of the Stone Age?
I don't know.
That we use stone to create tools. That was because stones are everywhere. And
Yeah.
certain stones, especially like obsidians, they can be chipped in a way that they make them really sharp. It's very important now because in the most of South America, metal was a rarity, the new gold, but iron and so on, even copper or bronze, unheard of. Because they had so much access to obsidian, which is a very sharp stone, they didn't really need to develop any metal. But in Europe, pretty early on, we moved from Stone Age to Iron Age or Metal Age, and
Mm-hmm.
we start using one of the first things we start using as a tool was copper. Copper, because copper is a semi, I would say, noble kind of metal that you can have uh, you can have actually copper as a copper nugget, and then you just have to melt it and then make tools with it. Um, Copper is very soft though. Then we discovered if you mix copper with some other alloys like thin, um,
Tin, you mean?
thin, then you get bronze. And then we have the Bronze Age.
Mm-hmm.
Have you heard of the Bronze Age?
Yeah.
Where we have a metal that is actually pretty hard. Bronze is so much harder than copper.
Didn't they use it for their gear, their fighting gear?
Yes, yes, that's exactly what they use. That in most of Egypt, they used a copper sword. And then somewhere times about 5,000 years ago, we discovered, or they discovered, that there is an army you cannot fight against because they have swords that they cut through your swords like butter.
Mm.
And then we discovered those people are using iron sword made of iron. And then even better, then they developed the so-called Damascus sword or Damascus iron, where they have it mixed with carbon, then becomes steel, which is much, much harder. Iron itself is not a very sharp metal.
Where are they finding these metals?
Very interesting you ask that. The first time that we had iron was actually a remnant of the asteroids because most of asteroids are made of iron.
Okay.
Either made of asteroids or made of either iron or ice. But if they are made of ice, by the time they enter the atmosphere, they're
Yeah,
just
tiny.
they're gone. They don't make it through the atmosphere. But those that make it through our atmosphere are made of solid iron. So the first sword made out of remnant of asteroid, and that was so valuable. It was so hard to make for a long, long time. Okay, but even at that time, we knew there are these minerals, these stones, these rocks that are magnetic. Long, long later, we discovered the reason they are magnetic is because they have a lot of iron in them, and the iron is locked in the rock in a certain orientation that the magnetic kind of force is fixed there. Now, the problem with regular iron is that because the molecules are in a metallic, they're so-called metallic um, bound, they're free, meaning each atom of iron is magnetic by itself. But if you align many of them in one direction, then you have a magnet, meaning more of the atom spin in certain way that they have direction to their north and south pole, magnetic north and south. And literally, in a regular iron is they can just move around and they cancel each other.
So if there's more atoms, does that make the magnet stronger?
Absolutely. If you have more atom and more atom that are oriented along each other, and that is what the supermagnets are. The supermagnet, they lock the, you know, um, they lock each atom in a way that they're all looking in one way. Like imagine you have 1,000 people that are pushing in one direction, okay?
Mhm.
They're so much stronger. Now you reorganize these 1,000 people, and for example, in a room or on multiple ropes, that they're pushing in different direction. They cancel each other out. But
Okay.
now, if you come with a strong external magnet, and that strong external magnet orient all these internal molecules of iron, like imagine somebody comes and very famous person, and all people now look in one direction and push or pull in one direction together, then their force is magnified. They're much more stronger than each person push and pulls in different direction. And that's what a strong magnet is. How do we lock all those individual people that they don't just turn around and push in different direction? Okay, that is what makes a strong magnet.
Okay. Can you break down the word magnet?
Break down the word magnet, where it's
Like,
come from.
yeah, like mag, what is it? Because I'm thinking magnify. Does magnify have anything to do with magnetic?
I honestly don't know. We should actually Google it right now. What the word, the origin of the word magnet is.
While you're doing that, while you're Googling it, what
Mm,
is like when you think of a magnet, like you have a souvenir magnet, the back, the magnetic part, or I don't know if it's the magnetic part. What looks like the magnetic part is always this black, thin kind of, it feels like plastic. Obviously, I know it's not plastic. What is that?
Um, no, I'm sorry. I'm just looking the word magnet. It says it's come from the a Latin word of push stone or something like that. I think originally the kind of stone that had this property
Mm.
were
Okay.
called that way. So it says a piece of iron or ore, alloy, or other material that has, this kind of the Latin come from uh, lodestone, a stone or a pebble or something that provide, it had some pushing or pulling properties.
From when? What year was that?
Oh, it says it's the old Latin, so
Doesn't
probably thousands of years old. That is,
before or after the pyramids, do you think?
I think that's after the pyramids. I think, in the time they built the pyramids, they didn't have iron tools, they have
Okay.
iron technology. So this must be much, much after that. Okay.
Okay.
So, um, coming around that, the reason that you can put a magnet on the cornerstone of your house where those iron is, even though iron itself is not a magnet, is that when you bring the magnet close, it really aligns the atom of that metal in a direction that it makes the other metal magnet. Now, in a regular iron or steel, as soon as you take it away, the atom just reorient themselves, and then again, even though individual atoms are magnetic, the randomness get rid of the magnetic property of the iron itself. And but I think what's very important here is that eventually we figured out how to keep that magnetic property still in place. Have you noticed that most of the magnet that you use, um, if you try to bend it, it breaks. It's not bending. It's not like a metal. Doesn't act like a metal. It acts more like a stone rather than like metal, even though it's made out of metal. But if you take like a regular bar magnet, and if you try to bend it, it won't bend. It will break. Have
I
you?
think I'm more used, no, I haven't noticed that because I think I don't really use the same types of magnets as you. You're definitely using magnets for different reasons than me. A lot of the magnets I have are like those thin touristy ones that are actually very bendy.
Yeah,
It's
yeah.
almost like a plastic.
They are actually not like plastic. They're actually in rubber. What they do,
Mm.
they put that individual, individual like small powdery material. They put it in rubber or plastic. They put an external magnet and then they cool it down, and the magnetic kind of property is fixed in place.
I actually used to own that kind of powder because I used to love doing my nails. And there's this nail technique where you can put that powder on your nails and then you get a tiny magnet and you can move the little powder around to make designs. Actually, it's
Then
really
you
cool.
and then you lock it in place with some lacquer or something.
Yeah, and then you put some clear polish over it and then UV light and stuff.
Yeah, and that is exactly what we produce a magnet. Otherwise, as soon as you let it be, they reorganize it and the magnetic field is gone. Now, most of professional magnet is done by having some other material that breaks um, the crystal property of a metal. Because in a metal, electrons are just freely flowing and the atom can reorganize themselves. You have to fix it in place. So either with other metal or other material or just carbon or something that prevent once you put it there, you put a strong other magnet, and then you either cool it down or heat it up or do something or put material like a lacquer or plastic to keep them aligned.
Okay.
And that's how you create the magnet. And I think much later we noticed there is another way of creating a magnet. Like that's a way that Vikings found out how they can navigate actually.
Okay.
Because Vikings, they used to have every few years, they had to replenish their what they had with raiding.
Mm-hmm.
That was their way of life. Now let's go. Next year we are going to go raid south, north, and so on. But then they became good navigators because they had to use their tiny, ships to go around. What they found out is that there's a way to make an iron needle so that it always look at a certain direction.
Okay, that makes sense. North.
Yes, yes, but do you know how they made that needle magnetic?
Oh.
They actually took some animal skin and they just rubbed it back and forth or rubbed it in one direction, and that is how you can make a actually needle. Still, you can make a magnetic. Like if you have nothing else, you take a needle and then you take a piece of cloth and then you rub it back and forth. You just rub it in one direction. Now, that is a true magic of the magnet that you have noticed that you get a balloon, you rub it against something, and then it becomes like a statically charged
Yeah.
electricity charge. And then you can hang it on the walls or some other places. You hold it against your hair and it pulls your hair and so on.
Yeah.
Have you
Yeah. Of
noticed that?
course.
Well, that's not magnetism. That is electricity. That is electricity. But the Viking figured out that with doing that just by trial and error, that if you do that, you make a needle magnetic. Then you put the needle on a small, tiny piece of wood on a water, so the friction is not really huge. And then that needle always looks in one direction, no matter where you are.
Hmm.
That is what they use for navigation.
That's really interesting.
Yeah, but that was exactly the moment that we found out magnetism and electricity, in a way, they're connected. Obviously, Vikings didn't figure it out. They were just interested in looting and raping and so on and so forth. So they just found out they were using it to find their way to go to a new village to pillage and rape. That's all they used it for. But later on, we found out that yeah, what if you rub anything like amber, you create electricity, something that a property that like what they literally did. And you know what amber is, right? Amber
Yeah.
is like a resin of some kind of trees and so on.
Yeah, actually, they just found a full dinosaur tail that's been preserved in resin, and it was like
Mhm.
very long and full of feathers.
Yeah, nice.
It was preserved in amber.
Yeah, but now if you take the amber and rub it against feathers or wool or animal skin, then you see that it attracts small little pieces of stuff because it has some static electricity. And amber, because it doesn't let the electricity flow, so the electrical charge stays there. Okay.
Okay.
And if you bring it too close, have you ever walked on a, like a carpet and then you touch
Oh,
something all of
yeah,
a sudden?
all the time.
Yeah.
Actually, when I was little, my sister and I used to turn off all the lights and shuffle around on the carpet so then we could see like the electricity sparks.
And then it's sometimes even better. One of you goes around on the carpet, the other one stands around. And then when you touch each other, actually a spark flies from one finger to another.
Yeah, we used to do that to my dad to bully him.
Now, the interesting part is that in 19 in 1600, 1700, we noticed that phenomenon and electricity are somehow connected.
Hmm.
1800, we actually understood a lot about it, and that the electricity and magnetism they're not the same, but they are connected.
Okay.
You can create with electricity, if you put it in a coil, you can make that coil behave like a magnet, even though if that coil is made of copper, a metal that's not magnetic. Okay.
Interesting. Yeah.
And then we found out that if you have a magnet and you move a wire against that, that can create electricity.
So is lightning attracted to all metals or just like metallic?
Hmm. Now you're talking about lightning in the Earth's atmosphere, right?
Yeah.
Okay. The different thing about lightning with the Earth atmosphere is that it has such a high amount of energy voltage. It doesn't matter what it is. Whatever is closer to the Earth, it jumps to it. It doesn't even have to be metal. But now you notice on the big buildings, we put a huge lightning rod.
Hmm.
So it gets that electricity and transfer it to the Earth because you don't want that electricity to go through the building.
Yeah.
Okay? If it goes through the building because the resistance in the building is higher, then it actually like heats up and explodes that. Whereas if you just put a piece of metal, the resistance is low, and then take the electricity from the atmosphere and send it to the earth without damaging the actual whatever building and so on it is. So we are still talking about the magnets and how we figured out that this interconnection between magnets and electricity.
Hmm.
And by the way, that microphone you have in front of you, that's how actually it works.
Interesting.
Okay? So inside of that microphone, there's a piece of magnet, and that piece of magnet, the round magnet, there is a coil around that magnet. That coil of wire, the copper wire, is connected to a diaphragm, like a small little membrane. And the voice from your talking, it vibrates that membrane with whatever frequency that it receives. Yeah, like when you talk, all your voice, all your noises you make are turned into vibration in that membrane. That membrane by itself, it vibrates against that magnet and produce tiny amount of electricity.
Hmm.
And the machine, the computer, and so on, it amplifies that electricity, digitize it, send it to my computer. My computer literally takes that electricity, send it to my speaker, which is the opposite. That is a magnet and a coil, and it sent that electricity to the coil. And because that coil all of a sudden become a magnet, not a permanent magnet, but a magnet that can repel or attract to the permanent magnet, and it makes that coil just vibrates, and that vibration goes through the air to my ear, so I hear you.
Interesting. It's
Yeah,
kind of cute.
yeah, it's very cute actually. So another thing that I think talking about the magnetism in your home is anything that has electromotor in your home works with a magnet.
Like a fridge,
Anything that has a
HVAC.
your even your hair dryer.
Mm-hmm.
Did you ever think how your hair dryer works?
Well, I know my hair dryer has like this. I have two hair dryers, and my really old one, it's from like the early 2000s. It actually has like a vent on one side where that sucks in the air and then blows out the air on the other side. And there's a fan in there. And I know that because if I get too close to my head, it'll actually suck the hair in on the wrong side and then get all twisted up.
Yeah, well, for that to suck the air, it has to produce airflow.
Mm-hmm.
And the fan part is that what really create the airflow. And there are some coils as well that heats up the air and so on. But main part of that hair dryer is that it's something like a fan that turns around. For to do that, your hair dryer has two different coils. It doesn't have a permanent magnet, but it sends electricity to those coils, and it creates a magnet in both of them that they repel each other. By repelling each other, and then it produces motion. Now the
Okay.
problem is that a magnet, there are two parts of a magnet, North Pole or South Pole. Opposite attract, same repel. But with the magic of electricity, we can make that once they repel each other, but imagine they repel each other, and then when it gets to the point that this is now the south part, the south come close, the pole change, and then change that they become again same kind of pole and repel again. So that is the advantage of electricity, that by changing the flow of the electricity, we can change the poles. So those pieces in your hair dryer, they always repel each other. So there will be a perpetual motion inside
Okay.
that
What
makes
about
the
What about screens? Are screens, do they have magnets like TV screens, phone screens?
Hmm, that's a very good question. The old screens that you probably don't even remember,
I remember they would be very staticky and you can like put your hand to it.
yeah, those old screens, like a vacuum tube, they weren't thin. They were like a truly
A
like a
box.
huge box. Yes. Now, there was a flow of electron that would come to the screen, but to guide that electron beam, that the electron beam would go line by line, right to left, and then up to down, and literally move the 25 times a second, would fill the entire screen, literally go line by line, and so on, and then go again up line. The way to send that electron beam to like a line that goes every single area of the screen, that was done with a magnet actually.
Okay.
But current screens are just work differently. They're so-called either light emitting LEDs or plasma and so on. So there, every electrical charge has a magnetic component to it, but the magnetism is not the main way to produce the light or the screen in the current, in the most recent ones. Okay.
Got it.
So what else in your house is having a um magnetic?
I think my AC, like my HVAC system.
Absolutely, absolutely. Anything that has electromotor has a, but in our lives as well, not maybe in your home, but there is another a process that we use magnetism a lot, and that is in medicine. Do you know what I'm talking about?
Like
MRIs.
blood stuff.
No, magnetic resonance tomogram, MRI, magnetic resonance
Yeah.
imaging, where that's actually a marvel of science by itself, where we create such a high level of magnetism, like the unit of the magnetism is Tesla, rightfully named after Nikola Tesla.
Mm-hmm.
And now the magnets that you have at your home is like a one fraction of a thousand of a Tesla. But when you go to like a imaging, when you have a broken arm, shoulder, bad shoulder, or brain tumor, God forbid, when you go to those magnets in the MRI, they are like thousands of times stronger than your usual magnet. They are so strong, as a matter of fact, that they make the hydrogen atom in the water align. So
Wow.
that those hydrogen atom that is usually not magnetic in a strong magnet becomes magnet-like. And that's a very complex kind of mechanism that when they all are aligned in one direction, that not all of them, as a matter of fact, 7 in 1,000 are more aligned in one direction in the magnetic field of MRI, 7 in 1,000, but that's enough. So they imagine now they're moving in this direction. Now, if you send it, depending on how strong the magnetic field is, if you send the electromagnetic wave, like a radio wave or something like that, they start processing. Processing is, imagine this is turning. This is just turning. I'm turning it back and forth here, right? Turning it.
Mm-hmm.
Procession is about not only turning, but the axis like a, have you seen those boys' toys that they put it on a surface and they turn it and it just
Yeah.
stays upright and so what
A
is it called?
dreidel.
Dreidel,
Dreidel.
yeah, dreidel. And then have you seen with like a dreidel, it can turn, but then sometimes it start pivoting around like that. We call that precession.
Okay.
And that precession, when they turn around, can be, depending on what amount of magnetic field is this hydrogen atom is, they can, when we send an electromagnetic wave, like a radio wave of certain frequency, it can put it in certain precession. Now, if you take that if you literally take that electromagnetic wave, radio wave away, they fall back um, to be aligned with the magnetic field and send the same radio wave back.
Hmm.
So depending on how much hydrogen molecule is there that is now moving in the precession, it sends that much radio wave back. And if you measure that, you can tell how much hydrogen molecule is in that location, specific location. And that tells you, for example, in your brain, if you have more water or more fat, and that literally helps you to get a picture of inside of your brain. That is high level scientific things, but the fact that it works is unquestioned because I think almost everybody had an MRI sometimes in their life.
Yeah, at some point.
Have you had an MRI? Have
Yeah.
you had the MRI?
Yeah.
May I ask why you got the MRI?
I was having like a lot of headaches and stuff, so I got a head MRI.
And when you are in MRI, can you describe it? Because you do,
No, I can't describe it because it was like 15 years ago, so I don't really remember what it was like.
but for most of the people who are there, you notice they fix something around your head. And that thing is what we call a coil.
Okay.
That is literally a coil, a wire that goes around your head. It gives that electromagnetic wave and it measures it back when it comes back. And most of people know as well. Then you go into inside of almost like a tunnel. MRIs are made. And that tunnel is made outside of that tunnel. There are lots of coils of more wires. And that's something important there. Those wires are cooled down to like minus 270. The only way we can cool those wires that far down is with liquid helium. Okay.
Hmm.
So why do we cool them down? Because when we cool them down, we reduce the resistance in those wires, then we can send a lots of electricity without heating them up. And we need a lot of electricity to create a lot of magnetism. Because what MRI does, it makes something that is not magnetic, like the hydrogen atom, it makes that non-magnetic material magnetic by just having a lot of magnetism. And those MRIs are usually 1.5 Tesla or 3 Tesla, which is huge, like to a point that, if you have something metallic there, it shoots like a rocket into that thing. That's why you cannot bring anything magnetic into an MRI room.
Yeah, I've always wondered why not.
Yeah, because it shoots like a projectile into that. But you need that high magnet to make something like a hydrogen atom that's not magnetic to magnetic. And then when you're there, people as well say they hear this clocking noise, clock, 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 clock. Those are actual impulses that the coil sent to bring those hydrogen atom to procession. Each of those clocks is a bunch of radio waves that is produced to makes those hydrogen atom, not to be aligned, and they give them energy to process against the equilibrium in the magnetic field. And that's what that clicking noise is in the MRI. People who have been there, they can usually remember that it is narrow, it is loud, and it's truly a little. Actually, most of people say it is not a pleasant thing to be in a MRI for that reason.
Yeah, I know they give you one of those things to squeeze, like to let them know if you need to get out or something, you're getting too
Yeah,
claustrophobic.
yeah,
Well, that's interesting how versatile magnets are from just a decoration to a medical diagnostic device.
yeah. So I think we did, for the most of the common purposes, we covered what the magnets are.
Yeah, I
So
think to get into the more technical purposes, we should do a separate episode.
you definitely should. You definitely should.
Well, thank you guys for watching. This was Essence of Science, and today we talked about everyday physics. And magnets. I'm Amanda Armagost.
And I'm Dr. Abbasi for Essence. Thank you for joining us.
Thank you.